Hello and welcome everyone. My name is Hannah Mason and I'm an associate editor at Composites World. I want to thank you for joining us today for this webinar titled The Future of Additive and Hybrid Technologies, brought to you by Composites World and presented by CMS North America and Diversified Machine Systems. In this presentation, our presenters will define additive and hybrid technologies, discuss how additive and hybrid technology are changing the CNC industry, and demonstrate the value that this technology brings to manufacturing and why companies should invest in it. We have three presenters today. As you can see, our first is Marty Sutten, technical specialist at CMS North America. Marty's been in the field of metrology and CNC technical maintenance for more than 25 years, making him CMS North America's premier metrology expert. Our second presenter is Nathan Dix, product development manager for the DMS Additive Technology Division. Nathan has been in the industry for 10 years and with DMS for more than 4 years. He holds a degree in welding engineering. Our third presenter today is Maurizio Bernini, product manager of additive manufacturing and new technologies at CMS. Since 1982, Maurizio has been on the forefront of technical and commercial development for technologies such as an industrial camera, and one of the first CAD/CAM CIM systems for the manufacturing and sale of furniture. He's been on the CMS Composites team since 2002. This discussion will last about 40 minutes, followed by question and answer. If you have a question, you can type it in at any time during the webinar in the Q&A field you can see on the right of your screen. The webinar is being recorded and when complete will be made available to you via email from Composites World as well. All right, presenters, it's all yours. Take it away.
Okay, well, good morning and good afternoon, depending where you may be. I am Marty Sutten. I'm from CMS North America. I'm joined here in Colorado Springs at the DMS manufacturing facility with Nathan Dix. He is the product development manager for additive manufacturing for DMS, as we mentioned, and also Maurizio Bernini from our factory in Zogno, Italy, in northern Italy. He is the project manager, as mentioned, for additive manufacturing and new technologies for CMS. Maurizio has been involved with additive manufacturing for a great part of his career. He has seen additive manufacturing come from its absolute infancy of printing small plastic gears up to large format area manufacturing that we're doing now that is really beginning to change how manufacturing is done, especially in the additive field. One thing about additive manufacturing and plastics, as are most of the extruded additive manufacturing is done, there are many, many, many different types of plastics, thousands of plastics. And everyone seems to like to make their own acronyms. So if you have a design or something different than anyone else, there is not a single acronym that denominates large area manufacturing or metal additive manufacturing. There are acronyms for every single thing. My part in this, I generally am a metrology and subtractive manufacturing specialist. So my position in this webinar is going to be more of a narrator. So I'm going to give a brief history on additive manufacturing, and then we'll go into some questions that I will ask Maurizio and Nathan, and we'll allow them to speak on their areas of expertise. One happens to be extruded manufacturing from Maurizio and CMS, and DMS does wire arc additive manufacturing.
Yes.
So again, there's many, many types. It's tough to keep up with all the names and acronyms. So let me get into a little bit of the history. I've just got a very brief outline of what we have. So the American Society for Testing and Materials has defined additive manufacturing as a process of joining materials to make objects from 3D model data, usually layer upon layer, as opposed to subtractive manufacturing methodologies. So some of the brief history of 3D modeling and 3D printing. Some of the first 3D modeling was really done in the 1800s. And again, I don't want to bore you with this, but it's nice to understand where we come from. So a lot of these, they were topographical dioramas. So what they did is when they started excavating ruins and the Egyptian mounds and all of these sort of things, they wanted to see a three-dimensional object of this. So what they made are topographical dioramas, which delineated through elevation. So they didn't really do additive manufacturing as we think, because we think of it as automated. But they were making models three-dimensionally so they could see the structure of the pyramids, what was left on the ruins of Pompeii, many other things, even cave structures, the Greek ruins, all of these were made up in a manual 3D modeling type. So as far as the modern additive manufacturing, most of the early attempts were made in the 1960s, and it was generally started because of materials developed by DuPont in the 1950s, where you could use heat or photo UV light to fuse plastic. So Hideo Kodama in Japan had the first patent in 1980. He applied for a patent, but it never got any commercial traction, so it really didn't go anywhere. So the real father of additive manufacturing is generally considered Charles Hull. In 1984, he patented the first commercially viable source of additive manufacturing, and it used two lasers that sintered plastic in a slurry of plastic particles. In 1988, these were the first commercial additive manufacturing systems installed in the world. So I'm not going to get into all of these, but there are very many different types of additive manufacturing, as we mentioned. So there are polymer additive manufacturing and methods, and some of these are stereolithography that most people have heard of, but there are many such as solid ground curing, 3D masking, laser sintering. In the metal side of it, they have direct metal depositation, metal powder depositing, selective laser cladding. These are all metal additive manufacturing. We talked about the extrusion process, which CMS uses, and Maurizio will speak about it in length, but there's all kinds of these. I won't get into those. They also had different types with adhesive, so they would actually put on glue and then put a piece of material onto that glue, and they could build up three-dimensional things that way also. Other ones were electron beam melting, direct metal laser melting, solid object, ultraviolet plotters. All of these are some of the earlier and some of the later ones. Just a quick note here, it mentioned this company called QuickCast in 1993. They produced an investment casting pattern, and the reason I bring this up is one of the CMS customers actually did this with drill bits meant for drilling in the earth, whether it be water. Primarily it was natural gas and oil, but they could go out in the field and they would have, say if the substrate or the subsoil changed from clay to granite, for example, but they would need a different drill bit. The company that we worked with, they were able to design a new head and email it to a machine with no human interaction, would make this new drill head out of styrene or styrofoam, either one. Then what they would do is they would encase that into a ceramic cladding. Then they would bake the ceramic to make it hard. They'd burn out the styrofoam or styrene, whatever they use for their mold or their pattern. They would burn that out. Then they'd fill it full of carbide. They'd cook it again, and then they would have a drill bit. So within a 24 to 48 hour period, they could go from an idea of needing a new drill bit to exactly the drill bit with the geometries needed. So this was a different type of additive manufacturing, but this was something that around 2000 I had direct involvement with. This is just a little picture of some of the different things. So some of the different additives they have, they'll have a powder bed and they'll have a laser source that will sinter. There's some other ones where they're doing layers. Some of them have a slurry, as I mentioned, with the laser source, and it will solidify upon generally melting or sintering the material. Then we get into the extrusion, which CMS does, and they have material, and we have a nozzle, and it is extruded out onto a platform, and we build from there. We have material jetting. This is similar, but it uses a different type of heat source. This can be used in steel also, where they do plasma buildups. Material adhesion. This is again where they'll put down a glue layer and they have a roller to compact it. And then electron beam is just another energy source where they work in a powder bed. So I'll just go really quickly through this. In the very beginning, most of them were photopolymers, so they were reacted by either lasers or UV lights. So this is 96, 97, 98. In 99, they started doing some controlled metal buildup. So this is basically a precursor to metal additive. Let's see what we got here. Some of the advances, like in 2007, they had a plastic selective mask sintering system, which had a mask, and you could sinter the entire layer at one time. Instead of previously, it was more like an inkjet printer, where it would be very slow and just do small sections. With a mask, they could put high-powered UV light, and they could build entire masks vertically quickly. So this is part of the evolution of the speed of being able to. 2008, one of the big breakthroughs is they had laser sintering for PEEK plastic, which is a very, very durable hard plastic, which is still very useful at this point. At that time, it took a 725 Fahrenheit temperature to melt this and to be able to do this safely and accurately. As of 2009, 2010, we're still at very small volumes, 3 feet by 3 feet, about a cubic meter, basically. Another thing that 2009, the start of Inconel printing in very small volumes, which is we will talk to about in coming up. In 2010, some of the people that really grabbed onto this additive manufacturing were hearing aid and dental usages. Precious metals, jewelries, and watches also use a lot of printed, very small objects. Even today, if you go to the dentist and you have a cavity in your tooth and you need a filling, back in the old days when I was young, they used to put some sort of metal in there and told you not to chew on it for 2 days. Now they put in it's a photoreactive polymer, and they'll have a UV light, which they will cure the filling in seconds, and the hardness of it is immediate. So it's virtually as hard as your tooth. They also do this with even dentures and bridges, things like this, where they have in-house, they will do a 3D scan, they will build a bridge, and they will print it on site, and they can make these very accurately and very good. And most of these are photoreactive type chemicals that they use. This technology is so new that the first three-dimensional conference, 3D printing conference in New York City wasn't held until 2013. So this is less than 10 years ago that they even had the first conference about 3D additive manufacturing and 3D printing. But things really, really started changing, at least in the polymer side of it, when the Oak Ridge National Laboratories teamed with machine tool manufacturer Cincinnati. They developed a polymer additive manufacturing material extrusion system that was expected to be 200 to 500 times faster than current additive manufacturing machines. So this really sparked our industry, and one of the reasons why CMS chose the path that it chose in our large envelope additive manufacturing is because this made it commercially viable. There's many different approaches to this, but the influx of money and effort by the national government through Oak Ridge National Laboratories has really, really changed the direction of large area additive manufacturing. Additive manufacturing became so popular as late as 2014, Home Depot, you could buy inkjet printers that are additive manufacturing things. And it's come to the mainstream of normal people. And then as probably the tail end of that, in 2015, Rolls-Royce announced it plans to flight test the largest ever 3D printed engine part. It's a titanium front bearing housing containing 48 airfoils, and it is 59 inches in diameter. Once this met the aviation regulations, now 3D printing is a part of commercially viable ways to manufacture parts. After 2015, which is only 6 years ago now, this is all technology that has been very explosive. So now some of the different types of additive manufacturing, or for example, powder bed fusion, powder feed system, plasma depositing, wire feed systems, continuous fiber extrusion, single continuous fiber placement. It kind of looks like a spider web, and this is very, very new and unique. And there we go from there. So with the history done, we will get right into the questions. And the purpose of the webinar is making additive real. So this is the approaches of our two companies to make additive manufacturing a part of day-to-day manufacturing. So why don't we start with Maurizio? And the first question that we have is, why do machine tool builders, why are they investing in additive manufacturing? What seems to, instead of subtractive manufacturing, why are they jumping into this realm?
First, thank Marty for your kind introduction, and thank to everyone to be here to attend the webinar. I will show you some slides. It is an abstract from SCM Group eCampus, that is, we are following the criteria of knowledge organization. And inside of the group, we try to collect the information about our job, our fields, our technologies, to make our people understanding well what we are doing. Here the answer: additive manufacturing is the youngest industry, as you said before, and with a very high growth rate. And this growth rate is due to the fact that it is very attractive for the advantages that is given. And also it is a green technology, green for the material and energy savings. As you have said before, we have inside of the group two different technologies, one on metal, that is wire arc additive manufacturing, and the other one is polymeric, that is large format additive manufacturing by screw extrusion, that is CMS, stands for screw extrusion additive manufacturing. Okay, in this timeline, we can see how young is the industry and also the technology. The first commercial patent, it is a commercial patent related to stereolithography, SLA, is dated 1984. And the first patent for FDM is 1988. But the start of the sales of 3D printer, FDM 3D printer was in 92. Okay, just to have an idea of how young is this industry, you can go back in years. The first Formula One with a monocoque made of carbon was in the 1981. This is John Watson on a McLaren MP4/1 that in this picture was running and winning the Silverstone Grand Prix. And in an interview, Watson said it was like flying in a Concorde if you even flew in a 707. If someone of you remember the old 707 and the Concorde, can understand what they saw at the time. But going back in the time, I can say that the milestone for the mass use of plastic is 1963. That is the Nobel Prize to Giulio Natta. By the way, the laboratory of Giulio Natta is in the Polytechnic of Milan, where I studied. And I have visited this laboratory that is still like that. But the queen of industry is the automotive industry. And you, I think, know very well that the start of the assembly line of the Ford Model T was in 1913. You can understand how many years passed from the automotive industry start and the start of the 3D printing industry. But is also fast developing. Now, I remember with stereolithography by Photopolymer are made the sole of sneakers, shoes, with technology not so far from this one. not with laser, but with a projector of UV light, with the direct liquid printing, continuously printing the sole. Our technology started, really, ARC started with the first patent in 1925, but the first commercial patent was in 1990. And as Marty said before, 2014 was the year when started the technology we are using in CMS, that is large format additive manufacturing by screw extrusion. I can say that is one of the latest technology. After this here, other technology was developed, supersonic jetting, something like that. But this is important because it is really fast growing. Until 2009, additive manufacturing was mainly used for prototyping. And the annual growth rate was 9%. Not bad, but in the period from 2009 and 2019, the annual growth rate raised to 28%, more than 3 times. Why? Because industry discovered that additive manufacturing could be used also in production for final parts and production equipment. And this was the development of the technology, development of the business, and the answer why we started investing in additive manufacturing, because it is a business. It is a business strongly growing and improving for its benefit also other businesses. It is clear. You can see it at the first sight. That is the correct answer. Okay?
Would you like to expound upon that a little bit in how DMS is using additive? Why tool builders like us are going into additive manufacturing?
Yeah, we see just a big growth in, as Maurizio already speak to, there's a big growth in demand for this technology, and we see an opportunity to cater to that.
Okay, so then for our next session, we'll start with Nathan on this one. And what do you see as some of the advantages of using additive manufacturing? Kind of as a lead into this, is it faster, cheaper, less material, more accurate, more flexible? What are some of the main advantages you see of your technology?
On the large-scale metal side, one of the biggest advantages we see is just a reduction in lead times. Even for simple small parts where maybe you could machine it out of 1 or 2 inch thick material, that's a lot of material to stock, and it might take a week to get that in if you have a good supplier. For a small part, we could probably print it in 30 or 40 minutes. So a big improvement, even in small parts. As you get to thicker materials, if you have any parts that would have to be cut out of, say, billet that is thicker than 12 inches, that's material you're special ordering that's going to take months to arrive. And, it might take us a week or 2 to print a part, but that is still quicker than waiting on that material. And then another huge saving is when we look at long lead time, low volume castings. We've had people looking at these machines that might have a casting that they need a quantity of 1, and it takes them 6 months to go through the design process, proving that casting out and getting a part in their facility where we can print that same component in a much shorter time. And then the final area is just kind of bringing those resources internal. Instead of relying on a casting shop or a special tooling shop or an external machine shop, if you bring this equipment inside, you're able to print more of those parts in your facility.
Another thing you may expound upon a little bit is right there to your left, your casting for your yoke and also your cover that you've made.
Yeah, and we'll speak more to those
later on.
Later on.
Okay. Maurizio, would you like to say what are some of the biggest advantages we see from extrusion additive manufacturing, especially the large format that we are pursuing?
Not so different from the one that Nathan said before. That is, this is the machine, a machine tool having coupled also with an extrusion head and having completely automated the material feeding. The first advantage is the build volume. In this diagram, we can see with a logarithmic scale for concerning the area and linear scale for concerning the height, the position of the build volume of the 3D printer on the market. And the large format additive manufacturing means to have much more possibility for the build envelope. The blue dot is the build envelope of the current solution, that is CMS creator areas. But potentially, on the right side, you can see the area covered by the strokes of our range. So there is a lot of possibility, and we will see this later. Material saving. This is a jig. I'm a simple machining jig. Usually a machining jig like that is made of, in this case it was made of aluminum, but often are made of epoxy table, milled. And using our price list, we have not a price list of production because we are not manufacturing machining jigs, but just when a customer is asking for an acceptance test for the machine, to buy a machine, we are forced to manufacture also the machining jig. The same machining jig we have 3D printed when manufactured by epoxy table and milled, bonded together and milled, had a cost of epoxy table of 640 euros. We spend to 3D print this machining jig 102 euros. That is much more than 5 times the cost. But there is also another aspect, that is the green aspect. When you have to produce, to manufacture a jig for or jig or lamination master or a mold, direct mold for a one-off production, after the manufacturing of the part, you need to destroy, to throw it in the waste. Consider that my estimation is in 2019, around 7 million of ton of plastic waste was finished on the sea, in the ocean. So it is a need of our world, of our society, to reduce the amount of used material, and this is a solid way to reduce the amount of material. 5 times less material is 5 times less cost, roughly, and 5 times less material to be wasted. Another point is due to the build volume, we have discovered that we are on the border with the usage of the current FDM 3D printers. That is, potential customers are looking at our solution as an extension of capability of an FDM 3D printer. This is an example, a real example, at a real customer. Sorry, it is shaded for a confidentiality reason, but it is an assembly jig. An assembly jig is a machine, an industrial machine, used to couple parts, in this case of a car. You have some bases that are moving, some reference surfaces where the part to be assembled is laid up, and then the machine is moving to join the parts. And if the joining is right, without any with the right tolerance, okay, the assembly go on. If it's not possible, the parts have to be or reworked or discarded. Okay, in this case, the point number one, the part number one is not so important because it is the base, usually made of aluminum. We have 3D printed this base, but it's not this the point because an aluminum profile milled with the right accuracy to get the geometrical plane is widely enough. But the part number 2 and number 3 are the two reference surfaces that are mounted on the base in quite in the middle end of the base of each side of the base. Okay, in the real life they are printed by FDM 3D printer, and they took 26 hours of FDM 3D printing. With our solution, they was printed in 2 hours, and they needed 3 hours of milling. Naturally, when they are produced by FDM 3D printer, they are quite finished. Just sanding is needed and surface treatment is needed. With our solution, as we will see before, the 3D printing is less accurate, but with the milling, with our machines for the milling, we can get the CNC accuracy on this part, and it is a very good solution. I think the advantages are really, really sensitive for the industry.
To add to that just a little bit, I have a real-world customer that is using, it's a hybrid additive manufacturing that he's kind of created himself, but he makes large composite molds for industry. A prime example would be wind turbine blades. So we all know that wind turbine blades are quite large. In some of his methods of making his plugs to make the molds, he uses an epoxy paste. So this epoxy paste is very, very expensive. And he has, normally it's done through a very elaborate pumping system with 55-gallon drums. It's very expensive. Each set of drums is anywhere from $5,000 to $8,000, and he'll use thousands of gallons of this over a year. He estimated in just some of his small experiments that he did, even a 10% reduction in the amount of usage to apply this finishing paste. If he uses, the example he gave me was $1 million a year he used of this paste. 10% alone is $100,000 just in the application, not counting the reduction in machining time, because this has to be removed to make the final plug to make the mold. So it's very, very real cost savings in different types of additive manufacturing. So let's go on to our next question. Where do you think hybrid machines, these are machines that have not only additive but subtractive or milling heads, where do they fit into the additive manufacturing industry? And Nathan, we'll start with you and see what you have to say.
There's a few different areas where they're a good fit. One of the first is still rapid prototyping. If the part follows good additive design guidelines, or if it's early enough in the design cycle that it can be designed for additive, these tools are great for prototyping. You're able to print a near net shape and then go in and machine the areas where you need the higher tolerances, just like Maurizio mentioned on the assembly jig. We also make production parts. These machines are quick enough and produce high quality enough parts that they're viable for production. We're not limited to just prototypes with low load cases. We're able to build parts that are suitable for production, and we're able to have material savings associated with that. And then one of the most exciting areas for me is building impossible parts. So with a hybrid machine, we're able to build parts that you can't really make with anything else. You could build half of the part, stop, machine some features on the inside of it, seal that in, and then keep going. You know, an example of that could be a thermal forming or injection molding tool where you have internal cooling passages built into the part. So kind of those outside of the box parts that you really can't make any other way are, I think, some of the most exciting applications.
Yeah, some of the early driving forces in metal additive manufacturing were for turbine engine blades, because the blades on a turbine engine come right post combustion chamber. So you have literally fire coming out onto the first few blade sections of the power section of the turbine. Without cooling, they would be melted into a pile of slag. So a lot of these internal cooling channels were done with 3D printing quite a few years ago. But these are some of the driving forces of internal components that you could not really machine, not being able to build it from scratch. So these are some of the other driving forces. Maurizio, take a shot at answering this question. Where do you think machines are working out in our area?
As I said before, the finishing operations are needed, and our machine is hybrid because we have additive manufacturing and milling. We have invented a sort of tool change, changing automatically with no human intervention automatically passing from extrusion to milling, because the extrusion head is moved directly by the electrospindle, and the electrospindle is able to pass from the mechanical tool to the extrusion head and vice versa with an automatic sort of tool change. But we need finishing operation. This is the finishing operation of the parts we have seen before, because our 3D printer is not so accurate because of dimension. We will see later with what it is the section. I have a slide dedicated to this. Okay, but I agree with Nathan that it's very exciting to have cooling channel inside of the part. With metal, we are not so, because we are on polymer, and polymer is not good for cooling and for heating the part.
Okay, thank you, Maurizio. We kind of touched on this just a little bit in our last segment, but Nathan, if you'd like to expand upon this a little bit, what are the type of parts that we see that are being 3D printed? I mentioned earlier the 3D printing was embraced by the precious metals industry, jewelry industry, watches, hearing aids, and dental. These were all very early adapters of this technology. What are you seeing some in your metal arc additive manufacturing?
So I've got some examples of parts here that we've actually built for some of the machine tools that we build here at DMS. The first one was a low volume 5-axis yoke for an additive manufacturing machine. The first yoke that we built, we made it out of plate steel, and the individual pieces were bolted together. This component has 7 individual pieces. One of them was an outsourced sheet metal part, and there's probably 20 or 30 fasteners in here holding this together. We had an opportunity to build a second one of these machines, and I thought that was a great chance to showcase our 3D printing capability. So this part was designed from the ground up. You can see it has the same critical interfaces as the traditional manufactured part. We took 7 parts, turned it into one. This part is about the same weight, and it's significantly stronger than our original part. Another application we have is these yoke covers that we print. We make probably 20 or 30 of these per year, and normally it would be machined out of billet that's 1.5 inches thick. That billet weighs about 25 pounds, and we're turning 12 or 13 pounds of that into chips. When we make it with our hybrid process, we start with a 4-pound build plate, which is this face here. We add about 3 pounds of 3D printed material to give us the depth of the cover. So all said and done, we have about a 70% material reduction, and the finished part is over twice as light as what a part would be machined from billet. And the process is fast enough that we're able to be competitive in the additive process. This part takes about 30 minutes to print. So it's a pretty quick process for us. We've expanded this. I don't have an example here, but we made one custom machine with a similar cover to this, but the cover was 6 inches deep. It was about 20 inches tall and probably 15 inches wide. And if we would have machined that from billet, that chunk of aluminum would have weighed 175 pounds, and we would have turned 150 pounds of that into chips. So we printed that cover. The finished part weighed 25 pounds, and it took us about 10 hours to print it. So we've had great success on kind of the lower volume production components with our machine.
Another good example is of the hybrid machine is that also has the machining. It has all of your face, your mating faces. It has all your screw holes and counterbores in it.
If we can show this cover again, it gets printed in this orientation. This is the bottom. And one thing that I do on the hybrid after we finish printing it is we machine this inside perimeter here, just a 1/4 inch deep, and I also machine this seal groove. But my big motivation for machining this inside perimeter is I'm then able to use that controlled machine surface to fixture off of for subsequent machining operations. So I don't finish machine this in the hybrid. As soon as I'm done, I print another one, but I'm able to take this out, flip it over, put it on a fixture, and then finish machine it in another machine. So it makes it way easier to find this part for subsequent machining operations when you're able to add datum edges to pick up off of.
Very nice. Thank you very much. Maurizio, would you like to elaborate a little bit on this? What type of parts are you seeing our primary customers approaching, and in what type of industries? Is it automotive? Is it trains? Go ahead and elaborate.
Not yet trains. Not yet. We are developing. We have developed a small material flow machine, but we are working on a high material flow machine. Simply, I share again the slides. We are on tooling. Our kind of parts is tooling, not final part as the metal additive by Nathan. Toolings, and you can see the advantages. That is reduction of inventory and waste reduction because you are using less material. Sectors, both, this is part of the course. We are on aerospace, automotive, and industrial machine. That is, again, the 61% of the growth between 2009 and 2019. This sector are looking at the additive very with a large interest. Toolings means also toolings for not just machining jigs, but what we are calling it model, that is lamination masters. And we have some customers that have used the part that we have printed for direct molding autoclave with not so bad results. I can say that.
Kind of add to this is I watched a webinar not long ago about the marine industry. So it was a 3D printed boat. And this was a large boat. It was about a 35 or 38 foot, if I remember. But if you understand how boats are made, you make a plug, which is exactly what you want to produce. From there, you have to make a mold. Then from the mold, now you can gel coat it, and then you start laying up with various different things, either from chopper guns to core mat, core material, balsa wood, all this. Then you put other layers on it. All of this, especially for one-off custom boats. Now, as Maurizio said earlier, now you've got this plug and this mold, and some of these are very, very large. What do you do with it? These are things that will last almost forever. It's glass fiber and plastic resin. So these things are a big issue as far as like being able to get rid of them. So what we've seen, and it's been embraced more in Europe from what I've seen in the webinars that I've watched, but they're doing direct 3D printed boats. And then they can do the laminations or whatever they need to do for their details. But it's allowing them to not have tons of waste of non-recyclable materials and being able to directly 3D print not only the time frame involved, the labor involved, but they're making very accurate, very strong boats, and they can be built through additive manufacturing to have the reinforcement areas specifically where they're needed. When you're just spraying chopper guns, inevitably they have areas that are too thick, too thin, you have no control. With a CNC controlled additive manufacturing, you have control, I wouldn't say to the thousands, but you have very, very tight control versus manual methods of doing this. So marine industry is one industry that is direct printing large envelope things more and more, and they're very much financially viable.
Marty, let me say just one point I have not specified before. Plastic material are not recyclable 100%, but we have a system to recuperate the material, and not completely, but with a given percent can be reused. Not 100% because it is a standard on additive manufacturing. So also from this side, we are on a green view of the technology. I would like to underline this point.
Very much so, and it's a very good point. Thank you, Maurizio. Okay, one more question we have. In the early years, we know additive was very slow. It was very small. They were really, in effect, they were adapting inkjet printers to print different parts. It has accelerated exponentially. Again, we'll start with you, Nathan, if you'd like to talk about this. What's been done to speed up the metal additive manufacturing?
There's kind of two areas. One area is on the additive process itself. We're using a wire arc based process with a solid feedstock. And with that, we're able to achieve deposition rates in different materials up to 10 pounds an hour, which is almost an order of magnitude higher than what's achievable with certain powder-based or laser-based systems. Another huge benefit of the hybrid system is we're able to actually kind of reduce the amount of time it takes to make a good part. We're able to produce good parts on the first run, where traditional additive-only DED systems, you might have to make 10 or 20 attempts at a part until you get the part produced. It almost turns into a development process, where with the hybrid capability, we're able to print a few layers, machine the part back flat, print a couple more layers. So with that kind of in-process machining and controlling of the Z height of the build with a subtractive process, we're able to keep the parts more dimensionally accurate. Also, if we make any mistakes during the build with deposition parameters, we're able to machine that layer off and keep going. So if you're on layer 300 of a part that you've been working on for 2 weeks and something happens, the part's not junk. You can just cut that layer off and keep going.
This might be a good example of high levels of depositing in material. So there's a lot of material here. This is quite robust and heavy. Maurizio, what's going on in the extrusion area for speeding up manufacturing, especially in the large area, and how fast the depositation is coming?
Our reference is our natural reference is FDM, and the secret is here. Our strand, the strand of large format additive manufacturing by screw extrusion, usually is a rectangular, has a rectangular section with a rate between base and height quite fixed, 4:1. This allows the small undercuts, but also allows the good deposition without collapsing the material. Also with the thermal conditions, the good thermal conditions. The width rate is depending on the height of the section, and also the material waste. The material used is given by the base of the section. That is, with a strand like that, with this section, the section in the middle, you are 5 times the build rate, but for the same part, the repeated part, you are spending 5 times the material. On the right picture, there is a scaled comparison between the section of the strand we are currently using, 4 base, 1 height. I am speaking about millimeter, not inches, and the section of standard wire for FDM, the filament, 0.25 millimeter. You can see visually that we are very, very, very more quick in the build rate when compared to the FDM. Naturally, we need operations for finishing. This is the secret. This is the reason, the main reason for the manufacturing of the same part taking not 26 hours as on FDM, but taking 2 hours of 3D printing and 3 hours of milling.
Okay. Well, an hour goes very, very quickly. So there are many, many, many other topics that we would like to touch on and that are specific to additive manufacturing. One I'm going to just touch on extremely briefly are materials. So materials, as far as the plastics and the polymers, if you can see the screen here, we're just going to talk about these for 30 seconds. But everything from high density polyethylenes to polypropylenes to polytetrafluoroethylenes, and you see why acronyms are quite popular in all of this type of thing. But these are a lot of the thermoformings. One of the biggest ones right now is the polyether ketone, a PEEK. It is shown great promise for great rigidity and stiffness in a lot of tooling and things like this. These are all of the thermoforming plastics. Thermosetting plastics are plastics that undergo a chemical reaction and become different after they've gone through heat. And then there's also the epoxies and all those, but you can see there are hundreds and hundreds of types of different plastics and their application. So these are something that we would have liked to have talked about briefly, but time is coming to a close. We'd like to open up for questions. If they have some questions, let us know.
Can I go with material, Marty?
Let's see what we have, see if we have some audience questions first, because we're down to about 5 or 6 minutes left. So let's see if the audience has something.
Can I answer or not? No, sorry.
We've got a couple questions coming already. Thank you guys so much. That was a great discussion. Yeah, so like Marty was saying, we have just a couple minutes now for questions for our presenters. So just a reminder to attendees, if you have a question, go ahead and type it in now in the Q&A field on the right of your screen. So we do have a few that we'll start with here. The first one, what are the current XYZ extents or dimensions of the wire arc additive manufacturing process?
Okay, Nathan.
The largest machine that we've built to date has a 6 foot wide by 12 foot long by 4 foot tall build envelope. One of the benefits of our process is it's not robot based, it's machine based. So we're really only limited based on the size of the machine frames. So we've got a machine on the floor here that is 20 feet long, 10 feet wide with 6 foot of Z-stroke. And if the part size required it, we could implement the wire additive process on a machine of that size.
And Maurizio, take this question to you, not specifically what we produce, but what is the large area format extruder manufacturing machine that you have ever heard of in your career?
The build volume, the current build volume that you have seen there is, sorry, I am not saying it in your units, but in European units. That is 2000 millimeter per 1800 millimeter per 800 millimeter. This is the build volume of Creator Ares. The development of the new machine proper for plugs, for instance, as you mentioned before, have a test part that is 8 meter long, 4 meter wide, and 2 meter high. I am sorry, but I am not the immediate conversion in full feet, but
most of our audience understands both. So
it is a Poseidon. The base
yes.
it is a Poseidon, so you can understand that is a machine tool good for plugs for marine.
I think we may have time for one more question. Is it possible to get one more in?
All right, great. So last question here then. Have you seen or perhaps worked on any thermoform tooling produced by wire arc additive manufacturing?
I'm not aware of any tools that are in production. It's still in kind of a feasibility type phase.
Okay, and I think as far as our webinar and our presentation, I think we're coming to a close. Is there anything else that we would like to? Do we need to go 2 more minutes?
Okay.
Okay.
Yeah, no. Yeah, thank you so much. We've so any questions that have come in that haven't been answered will be forwarded to the team to be addressed later. Just want to say thank you again to all of you presenters for the presentation today. We appreciate it.
And our family of CMS and DMS, we thank everyone for tuning in, and we will continue to give some of these informative webinars and appreciate your attendance and any comments. We'll all be available for emails and follow-ups, however we may help in your future endeavors and what you need to be able to produce, and we will come up with a solution for you. Thank you very much, and thank you again.
All right, from Composites World, thank you again to our attendees for joining us today. We appreciate you being here and hope you will join us again for the next Composites World webinar. For more information, please visit compositesworld.com, and have a good day, everybody.
Okay.